These are the answers to homework 3H. These are the definitions that you need to know from the assignment. Now to the questions. Question number 1, they ask you to calculate the mass percent of the solute in two different solutions. The first solution is 21.6 grams of sodium nitrate dissolved in 225.0 grams of water. Mass percent is the mass of solute divided by mass of total solution multiplied by 100, and the first answer comes out 8.76%. In the second one, you're dissolving 55.1 grams of sucrose in 478 grams of methanol, and once again, we'll take the mass of the solute divided by the total mass of the solution. Because the methanol's mass was only accurate to the ones place, then the mass of the solution in the denominator also accurate to the ones place. Multiplied by 100 gives you an answer of 10.3% sucrose. Question number 2 asks you to calculate the mole fraction of solute in each of the following solutions. That's going to be the moles of solute divided by the total moles of solution. In the first one, 4.50 moles of dextrose are dissolved in 21.50 moles of water. We take the moles of the dextrose divided by the total moles of the solution, and that answer comes out 0.173 as a mole fraction of dextrose. In question B, they give you 12.5 grams of naphthalene and 75.0 grams of cyclohexane. In order to get the mole fraction, we're going to have to calculate the number of moles of each of the components. So first, for the naphthalene, we'll use its molar mass of 128.18 grams per mole to convert it into moles. And then for the cyclohexane, we'll use its molar mass of 84.18 grams per mole to convert its mass into moles. To get the mole fraction, we'll take the moles of the naphthalene divided by the total number of moles of solution, and that's going to give us a mole fraction of 0.0987. Question number 3 asks you to calculate the molarity of two different solutions. Molarity is defined as moles of solute per liter of solution. In A, 1.58 moles of glucose is dissolved in enough water to make 5.0 liters of solution. So we're just going to take the moles of the glucose divided by the given volume of the solution, 5.0 liters. That's a 2 significant figure number. The answer will turn out to be 0.32 molar in glucose. In B, they have 15.5 grams of sodium chloride dissolved in enough water to make 1.50 liters of solution. In this case, we'll need to convert the 15.5 grams of sodium chloride into moles first. We'll use sodium chloride's molar mass of 58.44 grams per mole, and we come up with 0.265 guard-digit 2 moles of NaCl. Divide that by the volume of the solution in liters, we'll get a 3 significant figure answer, and the final answer, 0.177 molar NaCl. Question number 4, calculate the molality of solute in each of the following solutions. Molality is defined as moles of solute per kilogram of solvent. This is the only one of our concentration units where you're dividing by something about the solvent, not the total solution. In 4A, they're giving you 2.14 moles of fructose dissolved in 0.500 kilograms of water. We just take the moles of the solute divided by the kilograms of the solvent, and that ratio is the molality. This comes out 4.28 molal in fructose. B was a little bit more difficult. 27 grams of ethanol dissolved in 345 milliliters of cyclohexane. If we want to calculate the molality, we need moles of solute and kilograms of solvent. So in order to get the moles of the solute, we would take the 27 grams of the ethanol, use its molar mass to convert that into moles. That was not that difficult. But in the second part, I've given you 345 milliliters of cyclohexane. You need to know how many kilograms there are. So if you look at the conversion factor we just did on the PowerPoint, where we're converting grams of ethanol into moles, that conversion factor was the molar mass. What are the units of molar mass? Grams per mole. That converts between grams and moles. We're given the volume of the cyclohexane, but we want to know the mass. We need a conversion factor between volume and mass. And if you read the second sentence in question 4B, it says the density of cyclohexane is 0.778 grams per milliliter. Those units tell you that's a conversion factor between grams and milliliters. It means that 0.778 grams of cyclohexane equals 1 milliliter of cyclohexane. I'm going to use the density as a conversion factor between volume and mass, just like we use the molar mass as a conversion factor between grams and moles. So if I take the 345 milliliter cyclohexane, multiply by its density in the right way to make the milliliters cancel out, so the 1 milliliter on the bottom, the 0.778 grams on the top, we'll wind up getting the correct number of grams of cyclohexane. And if I divide this by 1,000, I would have 0.2684 kilograms of cyclohexane. So the moles of the ethanol divided by the 0.2684 kilograms of cyclohexane will give us the molality of 2.2 molal. Problem number 5 is going back to molarity solutions. Calculate the molarity of each ion present in each of the following solutions. The first one says the solution is 0.25 molar in sodium bromide. They want to know what the molarity of each of the ions are. Well, this is actually iron 3 bromide. I may have said sodium bromide. Iron 3 bromide is an ionic compound. When it dissolves in water, it dissociates into ions. From its formula, you can tell that when one formula unit dissolves, it'll produce 1 iron ion and 3 bromide ions. So the way you calculate the molarities of each of the individual ions in the solution is you take the molarity of the compound, 0.25 molar, and multiply that by the number of ions in the formula. So for the molarity of the iron 3 ions, it's going to be 0.25 molar multiplied by 1. To calculate the molarity of the bromide ions, it's going to be 0.25 molar multiplied by 3. In part B, the compound is magnesium nitrate, and the molarity is 0.44 molar. Magnesium nitrate's formula shows that it has 1 magnesium ion and 2 nitrate ions. When this dissolves in water, each formula unit will give you 1 magnesium ion, and so the molarity of the magnesium ions will be the compound's molarity, 0.44 times 1. There are 2 nitrates in the formula, so when one formula unit dissolves, it's going to release 2 nitrates per formula unit. So the molarity of the nitrates would be 0.44 molar multiplied by 2, and that gives you an answer of 0.88 molar in nitrate ions. Number 6 asks you to calculate the grams of sodium hydroxide needed to prepare 250.0 milliliters of a 0.400 molar sodium hydroxide solution. This is a solution where the molarity is given, so you're not solving for that. You're going to have to solve for a different variable in the definition of molarity, which is molarity equals moles over volume. So we know the molarity, we know the volume, we don't know the moles, so I'm going to multiply both sides of the equation by the volume, and we're going to calculate the number of moles of solute that must have been used to prepare this solution. When you now put in the molarity multiplied by the volume, the molarity can't be written as 0.400 capital M, because capital M is an abbreviation. It means moles per liter. So I'm going to write the molarity more explicitly as 0.400 moles of NaOH per liter. I'm now going to multiply this by the volume, and if the units are going to work out, the volume can't be 250 milliliters, it has to be 0.250, and I missed a 0, 1 extra 0 liters. This is going to wind up being 0.100 moles of sodium hydroxide needed to prepare this solution. If the question was how many grams of sodium hydroxide were needed to prepare it, we're just going to use sodium hydroxide's molar mass and convert the moles into grams. Final answer, 4.00 grams of NaOH. The last problem, number 7, has a chart they want you to fill out. And they've given you a little bit of data, and so we can plug some of that data in now. It says a solution is prepared by dissolving 25.0 grams of potassium fluoride in 80.0 grams of water, and the final volume of the solution is 110.0 milliliters. So I'm going to place those 3 values into my table now, and we're going to try to fill out the rest of the values. First, under the mass column, if I know the mass of the 2 components of the solution, all I have to do is add those together, and I'm going to get the mass of the overall solution, 105.0 grams. Quantity is what we measure in moles, and if I know the mass of my potassium fluoride, I can use potassium fluoride's molar mass to convert grams into moles, and I will now have the quantity of potassium fluoride in the solution. I'll enter that as 0.430 guard digit 3. If I know the mass of water, I can use water's molar mass to convert that into moles, and I can calculate there are 4.44 moles of water in this solution. I can enter that in the data table. And then finally, if I know the quantity of moles of solute and solvent, just add those together, and I can get the total number of moles of solution, which is 4.87, and then a 0.3 is a guard digit. So now the table is complete. The two blackened spots under volume we're not going to fill in because we can't do those. Let's go to the questions. A says, what is the mass percent of the potassium fluoride? So now we're going to sort of practice each of the calculations we did in problems 1, 2, and 3, and 4. Mass percent is mass of solute divided by mass of solution. So the mass of the solute is 25.0 grams, the mass of the solution 105.0 grams, multiplied by 100, mass percent 23.8%. B asks for the molarity of the potassium fluoride. That's going to be moles of potassium fluoride divided by volume of solution. So the moles of potassium fluoride are given in our chart, 0.4303, and the volume of the solution is 110.0 milliliters, which we're going to switch to 0.1100 liters. Divide these, three significant figure answer, 3.91 molar potassium fluoride. Part C asks for the molality of the solution. That's going to be, again, the moles of the solute, so the 0.4303 moles of Kf, divided by kilograms of solvent. The solvent, there's 80 grams of it. The kilograms would be 0.0800 kilograms. So moles divided by kilograms will give us our molality, and this one comes out 5.38 molal in potassium fluoride. The final calculation is the mole fraction of the potassium fluoride. So that's just going to be the moles of the potassium fluoride divided by the total moles in the solution. And that comes out, no units, because the moles cancel out, 0.0884 as your mole fraction.